In this segment, we'll talk about the composite trapezoidal rule and look at through an example. What the composite trapezoidal rule is a method of approximating integrals. It's sometimes also called the multiple segment trapezoidal. So this is the example which we are asked to solve for. And since we're using the composite trapezoidal rule, you also got to know how many segments you're going to use. And it's also asking for true error and absolute relative true error. That is mainly to get a glimpse of how good this composite trapezoidal rule is working. So let's go and write down the formula for the formula for the composite trapezoidal rule. So for an integral of a function f of x going from a to b, it is approximated as b minus a divided by 2n, where n is the number of segments, times the value of the function at a plus times the summation, which is basically calculating the value of the function at some intermediate points between a and b, plus the value of the function at b. So where h is, which is the segment width, is b minus a divided by n. So let's go and see how we can use this formula. So for our example, h will be equal to b minus a divided by n, which will be 1.3 minus 0.1 divided by 3, so it will be 0.4. And that makes sense because if I'm going to start from 0.1 and end at 1.3, I have three segments here. So the first segment will be 0.4 away from here, will be 0.5. Next one 0.4 again away, gets 0.9, and we have over three segments. So the integral going from 0.1 to 1.3 f of x dx will be approximately equal to b minus a divided by 2 times n, which is 3, times the value of the function at 0.1, which is f of a, plus 2 times summation I is equal to 1 to n minus 1. N is 3, 3 minus 1. F, a is 0.1 plus I, and h is 0.4. So keep in mind this is the argument of the function, plus the value of the function at 1.3. And from here, I'll get 1.2 divided by 6 times the value of the function at 0.1 plus 2 times the summation I is equal to 1 to 2, and the value of the function at 0.1 plus I times 0.4 plus the value of the function 1.3. And this one will give us 1.2 divided by 6 times the value of the function is 0.1. And now you got to now see that the series is going from 1 to 2. So there are two terms in the series. So I will put I equal to 1 first. And then for the next one, I'll put I equal to 2 to get my two terms of the series. And then I have my last term, which is 1.3. So don't forget about the 2, which is outside of the summation. So you have to bring that also. But look at the compact expression which you want to get now will be f at 0.1 plus 2 times the value of the function being calculated at 0.5 plus 2 times the value at 0.9 plus the value of the function at 1.3. So all we have to do now is to substitute the values of the function at these particular points and be able to find out what the answer is. So we're going to get 0.2 times the value of the function at 1 is what? 5. 0.1 e to the power 2 times 0.1 minus plus 2 times 5 times 0.5 e to the power minus 2 times 0.5 plus 2 times 5, 0.9 e to the power minus 2 times 0.9 plus 5 times 1.3 e to the power minus 2 1.3. So if we do all these calculations now, we'll get 0.84385 as the approximate value of the integral. Now to compare it with the exact integral 0.1 to 1.3 of this particular integrand turns out to be 0.89387, and you can do it as homework, and all you have to do is to use integration by parts to do that. So the true error in this case will be the exact value, which is here, minus the approximate value, which is, and so the true error is 0.05002. It's also asking you to calculate the absolute relative true error. That is nothing but the exact value minus the approximate value divided by the exact value times 100 if you're calculating in terms of percentages, and this turns out to be 5.59%. So giving you an indication that using 3-segment trapezoidal rule gave us a reasonable value of the estimate of the integral. And of course, if we increase the number of segments, we expect to get even better results than that. And that is the end of this segment.